Crypto for everyone. This talk is about Libsodium in PHP 7.2, but I'm also going to give you an overview of what cryptography is, the kind of functions that we use it for, how they're implemented in Libsodium, and what's different about that compared with other cryptography things that we've had in PHP in the past. So, to start from the beginning, what's crypto? Well, let me tell you all about Bitcoin. Actually, no, that's a joke. Crypto is about cryptography, which is from Latin, crypto meaning secret, graphy meaning writing. So it's about secret writing. Fundamentally, it's about writing messages that can only be read by the intended recipient. And we call that property confidentiality. Another thing that you might want to do is prove that it was you that wrote a message, and we call that authenticity. A flip side of authenticity is something called non-repudiation, whereas if you've proved that you wrote something, you can't simultaneously deny that you did. It proves that you wrote something, and you can't prove that you didn't. That's a problem, especially if you're using it for doing things like signing documents. It proves that you did do that. The other property which we're interested in is proving that a message has not been altered in transit or during processing, whatever, and we call that integrity. Now, each of these three properties, confidentiality, authenticity, and integrity, are roughly orthogonal. It's actually possible to have more or less each of them entirely separately, and you can use different measures according to which of them you actually want. Typically, though, you probably want all three, but it depends what it is you're actually doing. So, the fundamental question really is, do you need to use cryptography code at all? If we're only talking about serving your site over TLS, no, you don't. You don't need to do any of this. It's all taken care of by your delivery stack. Your web server will typically deal with all the TLS stuff, and for the most part, you don't have to think about that in your own code. You just get it to serve your PHP over TLS. But there are lots of other circumstances where you do want to do stuff, and the most common of those is typically authenticating users. You might be doing something more involved, like writing your own secure messaging app, or you doing something simpler like encrypting cookie values. Should you write your own crypto code? Well, this is a fairly straightforward answer. No. Or to put it another way, no. Don't write your own crypto code. There's nothing wrong with writing your own crypto code so long as you don't use it in public. Use established, tested, scrutinized algorithms and implementations, not homebrew stuff. Because unless you're a genius cryptographer, or even then, only after you've had the rest of the world validate and inspect your code should you actually use it in public. So don't write your own crypto code, use a library. So what kind of things do cryptography libraries provide? Well, we can divide things up, all the cryptographic functions that you might run into. We can divide them up into some groups, roughly, according to how many keys are involved in their use. At the start, we have, because we're programmers, 0 keys. And in this, we have things like hashes, pseudorandom number generators, and key derivation. And you'll find there's a whole load of algorithms with complicated and cryptic names like MD5 and SHA and Blake2 and Argon and all these things. Now, if you're not familiar with cryptography stuff, you might have absolutely no idea what these things are. And that in itself is a problem, because it means you don't know. You don't know if one of these is weak or strong or has problems or is slow or fast or inappropriate for certain scenarios. Then we have things like things that use one key, and these are typically message authentication codes and secret key encryption. Now, again, it's hard to know what's safe, and again, we've got a whole list of weird names like Blowfish and Poly1305 and Cha-Cha and AES. There's all these things that you might not have any idea what they mean, and it's difficult to tell what it is that you should use. Then finally, we have things that involve 2 keys, and that really comes down to key exchange and public key encryption digital signatures. And again, there's a whole load of weird names associated with these things. Some of them are not obvious. Some of them have these weird numbers in. Now, the numbers are actually quite interesting because I saw these things and it's like, well, why is it that number and not some other value, like poly 1305 and X25519? These are actually related to the prime numbers that are underlying the particular ciphers and cryptographic algorithms that are underneath them. Poly 1305 refers to a particular prime number, which is 2 to the power of 130 minus 5. And the 25519 is 2 to the power of 255 minus 19. That's much shorter than writing the number that actually is 2 to the power of 255, because that is a really, really big number. It's just a kind of a shortcut. There are also a whole bunch of functions which are effectively not cryptographic functions themselves, but they're related. And that covers things like encoding, compression, and mathematical operations. And so there we have things that you might be more familiar with, things like base 64, bin to hex, but more unusually things like hash equals. Now, there's been a long history of cryptographic functions within PHP. There have been a whole load of things that are in the core. So we've got things like mhash, mcrypt, OpenSSL, and then more recently things like password hash, hash equals, random number generator, and more recently Libsodium. And these things all brought different things to the party. Now, mcrypt was around for a very long time, and that has lots of cryptographic functions in. But unfortunately, it's also really, really old and crufty, and nobody's really paying it any attention anymore, and that makes it actually really quite unsafe to use. The password hash function introduced in PHP 7.2, that was a really important thing because it finally brought a consistent, straightforward way of using cryptographically secure hash functions to passwords. And that's something that previously had shown what a problem not having that was if you look at things like WordPress that classically used MD5 for its passwords, and not surprisingly this led to lots of sites being hacked because MD5 is rubbish for passwords. The random number generator in PHP 7 made the random number generation much more secure. Random number generation is an important feature in cryptography. The Libsodium extension actually existed in PECL, existed for several years in PECL before PHP 7 came along, of course. But so it's actually available all the way back to PHP 5.6. However, it was actually rolled into the base installation of PHP in PHP 7.2. So which extension should you use? I've already mentioned that mcrypt is really rubbish. And essentially, if you're typing mcrypt in an editor, stop. You're doing it wrong. OpenSSL is kind of middle ground. One of the problems with OpenSSL is that it really suffers from real legacy bloat, and it's just got an enormous number of functions in it, and some of them are really complicated, but some of them are also really old. But of course, when you're actually just looking at a list of functions, you can't tell which ones are new, which are old, which are safe, which are weak. You just can't tell. But on the other hand, if you're talking to something at the other end, which is also using OpenSSL, there's nothing really quite like it. If you want OpenSSL to talk to OpenSSL, then that's the thing to use. But tread carefully. If you're in control of both ends of the conversation, then Sodium is the obvious choice. Now that would apply to doing things like writing your own secure messaging application, or doing things like encrypting cookie values, where, although I say both ends of the conversation, in that case, both ends are actually in the same place, because typically you encrypt, send stuff to the client sends stuff back to you, and you decrypt it. So you encrypt and decrypt in the same place. But it means that you're still in control of both ends of the processing. Now, beyond extensions and core support, there's also a whole bunch of PHP cryptography libraries, which are, of course, written in PHP. Pair has a whole bunch of cryptography functions. PHP seclib is quite an extensive library. It provides lots of features and implements some high-level protocols like SSH on top of the basic cryptography functions. However, that particular one is actually based on mcrypt, so you shouldn't use it. There are some other ones, significant ones, like, for example, Zen Framework has its own built-in cryptography libraries, and those are pretty reasonable. You'll see this name Paragon, these guys here. This Paragon, I can't remember what the IE stands for. Paragon is run by Scott Arkazewski, who we'll mention in a minute, and he has several really useful and significant libraries. Sodium Compat is very interesting. It's a complete implementation of Libsodium itself, but written in PHP, which means that you can just load it into a system which doesn't have it as an extension. Halite is a little bit like PHP seclib in that it provides implementations of some higher level things like SSH on top of sodium compat and sodium itself. Just the other day he released this thing, Cipher Suite, which is a really nice little thing. It's to help you store, you've probably heard about things in conjunction with GDPR about having encrypting data at rest. It allows you to do searches on encrypted data. Which is quite a clever trick, which essentially involves encrypting the things that you're going to be searching for and indexing the encrypted versions of them, knowing what it was that you encrypted in the first place, which means that later on you can come and do searches that will match those fields, even though you can't actually see the content itself. That's really quite clever, and he's wrapped it up in this library. So there's a whole load of things, but generally speaking, you should prefer extensions over libraries, just for performance reasons. Cryptography stuff can be quite CPU intensive in particular. So if performance is particularly critical, aim for using the extensions rather than libraries. So what is Libsodium? Well, it all stems from this thing called SALT, which is a library called NaCl, which is the networking and cryptography library. And it has a nice website, nacl.cr.yp.to, so it's SALT crypto. And it's intended to be high performance, legacy free, heavily scrutinized open source C library for cryptographic functions. And in particular, it's resistant to many forms of attack in the things that it's chosen to implement, and it's also quite heavily defended against side-channel attacks. Libsodium is a fork of SALT. It's also open source, which you can find at libsodium.org. It's relative to the original SALT library. It's supported on more platforms. It's got bindings for more languages, and it's also had its code audited. So that's an important factor if you're doing cryptography stuff. Again, it's been available in PHP via PECL, but it's now standard in 7.2. And there are, of course, some people behind this. Something I didn't mention there. Libsodium is actually also available, as well as being available in C, which is how the PHP extension is built. It's also available in JavaScript and WebAssembly, so you can actually use it client-side as well. Although you have some different problems on the client side, especially involving key management. Because there are people behind all this. SALT itself is a product of, in particular, this name, Daniel J. Bernstein, known as DJB, Tanja Lang and Peter Schwaber at the University of Eindhoven in the Netherlands, and lots of other people. And Libsodium is mainly the product of Frank Dennis, who's a developer and photographer from Paris. He wrote the pure FTP server, amongst other things, and he's been a very long-time contributor to PHP core. You'll find his fingerprint all over anything to do with cryptography within PHP. Scott Arkaszewski, you'll find him on Twitter as well. He's contributed an awful lot of extra stuff around the sides of Libsodium, in particular documentations, articles on how to do encryption safely, particularly in PHP. And you'll find lots of examples of how to use Libsodium on his website. We'll get to documentation later. So, I mentioned side-channel attacks earlier. Now, it's fairly likely, if you're not into cryptographic stuff, that you don't know what a side-channel attack is. Well, the Wikipedia definition is this: any attack based on information gained from the physical implementation of a system rather than weaknesses in the implemented algorithm itself. And that's why I like this picture here. The gate is great. It's perfect. It does exactly the job it is intended to do. However, the way that it's been implemented means you can just walk around it. So it completely fails to achieve the level of security that you set out to do. But it's not the gate's fault. So what does these actually manifest themselves in practical senses in software? It really refers to other ways that information can be extracted from a system that are not quite what you might expect. And the most common ones of those are timing, thermal emissions, RF emissions, light, sound, and power consumption. There are all ways that systems leak information, often in very subtle ways, that can actually result in people being able to extract data from places that they shouldn't be able to extract data from. Recent examples of that have been extremely high profile. The recent Spectre and Meltdown vulnerabilities in pretty much all Intel CPUs, they are effectively a timing side channel. that allowed it to basically get access to memory that it shouldn't have been able to, corrupt things and obtain information that shouldn't be obtained. Another simple example I saw, which was really quite funny, this was some years ago. You get Ethernet switches, they have little lights that blink on and off. Cheap switches, what they do is they just connected the LEDs on the fronts to the data lines. And LEDs switch very fast. And so if you could just read the lights, you point a light sensor at them, you could just watch the data and actually just have the data pouring out of the port into the LED, out of the LED, and you could actually just read the data that was on the network without actually having to be physically connected to it. That's a light emission side channel attack. Now, timing is really the critical one and the one that you're actually most likely to run into. So here's an example. This is some PHP code which is vulnerable to a timing side channel. It's also done old style. So we're creating a password with, we're hashing a password that's been submitted by a user, so presumably this is some login page. We then do a MySQL lookup where we select from the database, and you notice that we're matching the email address, which is fixed for now, and the password is just the one that was passed in, that was this hash. Of course, we're not escaping it, but that doesn't really matter because it's only a hash. But of course, you should normally. Now, the critical thing here is that this comparison between the password field in the database and the passed value is done by the database. And the problem there is that the database is optimized for speed. So if you imagine we've got two strings, there's the one that we're comparing against and the one in the field in the database, and we're going to compare these side by side, character by character. And the thing is that the database's interest is to be able to return from this as fast as possible. And so it compares first characters, they might match. Second characters, they might match. Third character doesn't match. So it returns immediately. But then, say this password's quite long, and all the characters are correct apart from the last one. That one's going to take very slightly longer to return from this function call. And if you do this a sufficient number of times, it's actually possible to guess the password character by character by just doing often millions of requests. So this is why you need to look out for things like locking out people that make too many password guesses. So this is a side channel attack that leaks information through the timing. But there are better ways to do this. So this is how you do it safely, using standard PHP. Now, the query that we've got here, you'll notice that it doesn't have a comparison with the password. It just fetches the whole record that matches the user ID. This is actually vulnerable to a user enumeration thing that it will tell you if this value here was being passed in, you could use it to tell whether users exist on the system or not. But generally, that's probably not quite such an interesting thing as their password. We fetch the whole row, and then we run it through this function here, password verify, which compares the passed-in password that we used with the hash that we had stored in the database. Now, this function here, password verify, has been very carefully written so that no matter how long the passwords and however well or badly the passwords match, it always returns in the same amount of time. This is known as a constant time function, and that means that it's immune to a timing side channel attack. It doesn't matter how long or complicated it is, it will always take the same amount of time to return. So that means it's deliberately inefficient, but it also makes it more secure as a result. Now, to do the same thing in Libsodium, we have this function here. Libsodium, you'll find, is quite keen on long function names, but it's pretty much the same thing. So it just has a constant time function, which is the sodium crypto, which is the prefix that's used on all of the functions, followed by the password hash string verify. And then again, we pass in the same values. So it's essentially the same as the built-in PHP one. So, first up, hashing. Hash algorithms are designed for different purposes. So we typically have small ones, which are often used for binning or distributing things across sort of bins of say, for example, a classic use of this would be distributing keys across a cluster of memcache servers. You would use something like the FNV hash for that. Then you have fast ones, which are typically used for checksumming and verification. Say, for example, if you've downloaded an ISO image of an operating system or something, you might want to check that it is actually the same file that you intended to download. Or if you've got 200 gigabyte files on 2 different servers, you want to check that those files are the same without having to actually transfer one to the other and compare them side by side. You can just take a hash of each one at each end, and you want that to happen as fast as possible. But then you have slow ones that are more appropriate for password hashing. Things you don't want a fast hash for a password, because that means that they're easy to crack. Crackers can run them on GPUs and things and test often billions of password combinations per second. You want password hashes that are really slow, because when you're checking a password, typically you only want to know whether it matches or not, and you don't mind if that takes 100 milliseconds. Whereas a fast hash like Blake2 or MD5 will take almost microseconds to do the same thing, which means that you can run it millions and millions of times in the same amount of time. And that, to a cracker, means that it's easy for them to crack your passwords. Now, with all of these algorithms, there are typically reference implementations. So, for example, SHA-2 has there are several hashes of different sizes in the family of SHA-2. The most common one probably is SHA-256. But there are important distinctions within the sort of family of SHA-2 functions. Now, SHA-256 is actually the reference implementation, which I think was written by Daniel Bernstein, is actually a 32-bit algorithm. And that means that if you run it on a 64-bit processor, it's actually, relatively speaking, inefficient. And what you really want is a 64-bit algorithm. But as it happens, within the same family, there's SHA-512, which is originally implemented. Its reference implementation is 64-bit. And that makes it quite a bit faster and more efficient. So what you can do is you can take SHA-512 and then truncate it to 256 bits. You will actually get a different result. But that doesn't matter so long as you use that approach consistently. You'll get a 256-bit hash with the efficiency of the SHA-512 algorithm. More recently, there's been this new algorithm for passwords called Argon2. And there are 3 variants of this. Argon2i, which is resistant, particularly designed to be resistant to timing sidechannel attacks. Argon2D, which is designed to be resistant to trying to be cracked on GPUs. It has things that make it difficult to parallelize massively, which is the main reason that people use GPUs. If you've got a GPU with 512 processors on it, if you run something like MD5, you can test it on all the cores at once. Argon2, the algorithm makes it difficult to do that kind of scaling. And then finally, Argon2ID, which is a slightly more recent version, actually combines the two. So you get timing side channel resistance and GPU resistance from the same algorithm. So really, if you're writing a new application, you want to use the strongest thing that's available. And to upgrade from a lower quality hash to a better one, you can rehash when people log in, because at that point you've got the password in hand, so you can calculate a new hash, restore that in the database, and then next time it's going to use the stronger hash. So how do we hash things in Sodium? Well, in PHP we've got, say, a short hash. So this is for something like little checksums on communication packets, something small. The hash function in PHP gives you access to a whole long list of maybe 30 or 40 different hash algorithms. And again, this is a situation where you probably don't know what those hash algorithms do. I don't know most of them. There are lots of things with funny names and different numbers after them, and it's really not particularly clear whether these things are strong or weak or new or old. They're just a list of funny names. So it's left up to you as a programmer to choose one, and that means you're open to error. So Sodium provides this function called short hash, and it has a hash which is appropriate for that sort of circumstances. In fact, the short hash calculates a 64-bit hash, so it's unsuitable for things that are not going to be cracked or something, but they're nice and fast and effective. But the key thing is it gives you no choice of the algorithm. It just does its own thing, and that's it. The basic theme behind all of Sodium stuff is to remove choices from you. It takes away the opportunity for choosing the wrong thing. So if you can't choose a thing, you can't make the wrong decision. This is fundamental to all of these things. You'll find that in almost all the functions, it doesn't give you any choice about algorithms and things, or very little choice. Or if it does give you choices, then none of them are bad. So, then we get on to the fast hashes. The main thing it has is this thing called generic hash, and this is a replacement for things like MD5, SHA1, and also many of the things in the hash function. It just has this thing called generic hash. You just pass in a string and it gives you back the hash. Internally, it uses this algorithm called Blake2B, which is considered to be as strong as SHA3, which hasn't been deployed much, but it's actually faster than MD5. So that's a nice hash algorithm to use. Finally, password hashes. But the password hash is the one you saw earlier. It's the crypto password hash string. And that uses Argon2 ID, which is currently the absolute state of the art as far as password hash algorithms go. Now, in PHP, the password hash function currently uses bcrypt as the password hash function. And bcrypt is still pretty good. Argon2 is better, but bcrypt is okay. And PHP 7.3 actually adds support for Argon2. However, it has some problems, which I'll get to later. But if you use Sodium, it means that you can use Argon2 ID wherever it runs, which, because it's now in the base install, means you've always got access to it. So now we get on to the things with one key. First of those, message authentication codes. I particularly like this image to illustrate this. The idea of using a hash to authenticate something is problematic because a hash can be calculated by anybody. You can just go, here's this ISO image, I tweak the contents of it, and I'm going to just recalculate the hash and paste it back onto their website, and they'll be none the wiser that this has been altered. So this is the equivalent here of this wax seal. It would be the equivalent of somebody breaking it open, reading stuff inside, modifying it, sealing it back up, and just remelting the wax, and nobody would know. But here, we're adding this seal, which means that if somebody breaks it and remelts it, we would know about it. So it adds this stamp of authenticity, and that's the thing that message authentication codes give you. Just like a hash, but it also uses a key as well as the data that you're hashing. And typically this is used for authenticating or providing signatures on messages. And the most common of these is this algorithm called HMAC, which is just very simple. It's the hash-based message authentication code. And typically the HMAC algorithm takes a hash function and just wraps the key stuff around it. So you find things like HMAC MD5, HMAC SHA256, and so on. There's also this other one which you saw a reference to earlier, Poly1305. That's effectively a MAC function. It's not typically used by itself though. It's actually used as part of a cipher suite, which we'll get to later. So how do you use MACs in Sodium? Well, PHP has a built-in function for doing MACs called hash HMAC, and Sodium's equivalent is called Sodium Crypto Auth, because it's just about authentication. So here we can see that PHP is using the hash HMAC function, and we're telling it that we want to use SHA512 as our hash function inside it, and we give it the message, and we give it a key. Now, here I'm actually saying that I'm actually going to cut it down to 64 bytes of output. The Sodium Crypto Auth function, you notice that one thing is missing. We don't have the name of the hash function because it takes that choice away from us. In fact, internally, it actually uses SHA512/256 that I mentioned earlier, which is the truncated SHA512, which as you can see is exactly what I did here, except manually. I just cut it down from the 128 bytes it would normally be down to 64. Because the Sodium implementation does that anyway, we don't have to worry about it. The other difference with the Sodium one is it actually gives you the answer back as a binary string. So it's actually the raw binary value of the hash rather than it being a hexadecimal representation of it. So just to make them look the same, I'm applying the bin to hex function here, and you actually get exactly the same result out of those two. But this is something I'm actually quite keen on doing. In things like MySQL, MySQL is perfectly happy storing raw binary values. You can put things into binary fields. And they have the advantage that they're half the size of their string equivalents. And that means you can get twice as many records and twice as many things in your index into the same amount of memory, which just makes things faster and more efficient in general. And it's really quite easy to cope with. Now, relating to the MAC function is the use of hash equals. Now, this is exactly like the password verification stuff we looked at earlier, but here this is just a straightforward comparison between two hashes, and the hash equals function and the sodium crypto auth verify function are both constant time functions. And again, in hash equals, we do have to provide the name of the hash that we're using, as well as the message and the key that it was signed with. But in the sodium version, we don't. So it actually makes it a fair bit simpler because that choice has been taken away from us. And internally, again, it uses the SHA 512/256 algorithm. Right. Now, aside from the unfortunate British slang meaning of this, these are actually very simple. A nonce is a number used once. Now, typically, these are random or pseudo-random numbers, often containing a timestamp, because that's quite a useful way of making something that doesn't repeat. And these are used all over the place in cryptographic scenarios. So if you've ever used HTTP digest mode authentication, just the basic, or it's not the basic one, it's the digest authentication in the HTTP standard that's been around for, whatever, 20 years, you've used nonces, whether you knew it or not. And one of the most important things about them is they prevent replay attacks. If you've got an attacker that's able to listen to the traffic between a client and a server, a replay attack is where they record all of this information and then play it back later. And that might allow them to, say, log in when the real user isn't around. For example, that would be a typical thing to try and do using a replay attack. But if you have a nonce where each time you submit this, it's actually going to have a different one of these numbers, because the numbers are only ever used once. So although it might be the same request, you're expecting it to have a different nonce value, so it should never be reused, and that prevents it being used again. Nonces are actually what Bitcoin miners are looking for. When Bitcoin miners just sit there and churn away through these things, they're actually trying to figure out the nonce that was used to sign a particular block. So it's kind of trying to decrypt stuff. And the problem is that the algorithm that's used inside Bitcoin is really pretty strong, and it's really hard to find this number, which is why Bitcoin mining is so expensive and why it's considered a valuable commodity. And that's the complete value proposition of Bitcoin. It's also used as an initialization vector in encryption ciphers. And these are really things like it's like a starting point. It's like a seed for a random number generator, really. A lot of ciphers are actually really effectively just really good random number generators that will respond in a particular known sequence. So it's actually in some cases quite difficult to tell apart an encryption cipher from a random number generator. It's quite a useful thing. You can actually use a cipher as a random number generator if you don't care about the input. And because of this, they're used extensively in both secret and public key encryption. But the most important thing about a nonce is you never ever reuse it, especially with the same key. How do you make a nonce? Well, it's actually really easy. PHP has a really good function that was introduced, I think, in PHP 5.5, which is just called random bytes. And you just say, give me a chunk of random data. And PHP 7 introduced a really good random number generator, and so that's what's used to generate this data. And it's just a chunk of noise. And it's nice, solid, proper noise. It's got no discernible patterns to it. There have been lots of analysis of random number generators, and this PHP one is actually really pretty good. So it's perfectly okay to rely on that, and Sodium doesn't attempt to replace it because there's nothing wrong with the one that's in PHP. Reuse of nonces can be completely fatal. I don't know if you've heard recently, there's an attack on WPA2 encryption that's used commonly in Wi-Fi. The attack's called crack, spelt with a K. And that actually works by forcing the reuse of a nonce, and the net result is that people are able to guess passwords. And that's a really severe problem for something that's meant to be secure. One of the things about a nonce is that we've said, oh, it's a number used once. Well, how big is this number? How big a number should we use? And that's an invitation for you to guess. And if you guess, you'll probably guess wrong. And so again, Sodium deals with this by providing a whole bunch of constants which are appropriate that give you the appropriate size of a nonce for the particular context that you're using them in. So, to secret key encryption, this is another thing like a Mac. It uses a single key. So it encrypts and decrypts using the same key, and this makes it called a symmetric cipher because it is very symmetrical in its basis of its processing. And one of the things is that just because you've encrypted something, it doesn't actually guarantee either integrity or authenticity. Anybody who's got the key can make something and so on. And the other thing is that for the integrity side, somebody can encrypt something, you can tamper with the encrypted content, and you won't be able to tell if that corruption is actually from the original content or whether it was introduced afterwards. You have no way of telling because there's no integrity checking within the concept of encryption. That's why I was saying at the beginning that these things are more or less orthogonal. You can have one thing without the others. So what you need to do is, in order to guarantee this, is to stick a MAC on top of it. And that provides the authenticity because you've got the key there is used to provide a signature which will not match if you alter the tiniest thing in it. And if you know that that key that you use to generate the MAC has not been exposed, then it means that you know who did it. So, Sodium provides a whole bunch of functions called secret box. There's a whole family of them. And what they do is they provide a combined encrypt then MAC. And it's important that things happen in that order, because otherwise, if you did it the other way around, of calculate a MAC and then encrypt the result, in order to verify it, you'd have to decrypt it and then calculate the MAC. Now say the thing that you were decrypting was really huge, and it might take a long time to do the decryption. You're much better off calculating it, doing the encryption first and then MAC afterwards, so that when it comes to decoding it all, you can calculate the MAC on the encrypted data, and you don't have to bother decoding it just to check that its integrity and authenticity are intact. It also means that if it contains some potentially dangerous code, say, that somebody is trying to infiltrate your system, it means that you can know that it's bad before you even decrypt it. There are some other functions called AEAD. Now, this is sort of getting more into slightly trickier cryptography functions. And this really achieves pretty much the same thing as the secret box functions, except instead of applying an encryption and then a MAC process, it actually combines the two into a single operation. And that uses some specific ciphers that actually have this signature ability built into them. And the two that are available in Sodium are called CHARCHAR20 Poly 1305 and AES 256 GCM. And these are both examples of what are called AEAD ciphers. And AEAD stands for Authenticated Encryption with Additional Data. And the actual practical upshot of all this is that you encrypt something, and then you have a chunk of other data that's not encrypted that you just tack onto it. And then you calculate a MAC on the whole lot. And it's like, well, why would you do that? As it turns out, that structure is actually extremely handy because you can pass the nonce as part of the encrypted the whole package of data, and you'll see how we deal with that. These ciphers you may be familiar with. Both of these are commonly used in TLS. So you might find that if you do an inspection or run something like Qualys SSL Labs on your website, you might find these listed amongst the algorithms that are supported. These two are particularly interesting. CHARCHAR20 Poly 1305 is an AEAD cipher that was written again by Daniel Bernstein. And one of the things about it is that it's very, very efficient. It's extremely fast on low-powered hardware, so it's really good on things like mobiles and on embedded systems and so on. It's small and fast and efficient, and it doesn't require any specialized hardware. AES is an extremely common algorithm. It's used widely, but it's much more CPU intensive. However, what's happened is that Intel added a whole bunch of instructions that make AES effectively hardware accelerated, and that's made it much more efficient. And on desktop machines, AES 256 is faster than CHARCHAR20 Poly 1305. But on a mobile, it's probably faster to use CHARCHAR. Now the problem is that when you're ordering things for TLS, you can choose the order of these ciphers. So which one you get is up to the server config. And it's actually a kind of slightly difficult decision which one that you choose to do first. But essentially, if more of your clients are mobile, you're better off with Char, and if more of them are desktop, you're better off with AES. So how do we actually use secret box encryption in practice? Well, first of all, we generate a key and a nonce, and a key is just a random string. It's like having a really good password generator that produces a totally unreadable thing. I notice that the random bytes function returns just raw binary data. It's not pretty. If you printed the output of that, it would look pretty bad. So all we do is we pass in to the secret box function the text that we want to encrypt, the nonce that we just generated up here. Notice that we've got this secret box nonce bytes constant telling us exactly how much data to produce, and similarly for the key bytes. So we give it the nonce and the key. An alternative implementation is using the AEAD thing, the CHA-20 poly 1305 encrypt function. Now, because it's this AEAD cipher, we provide some additional data. And as it happens, it's quite convenient to provide the nonce. So you can see we actually just provide it twice. It's the same piece of data, but that's fine. And so this gives us, either way, some encrypted content. Now, when we transmit it, to decrypt it, we also need a copy of the nonce. But that's fine. The nonce is just a number. It has no particular significance itself, other than the fact that it's used to initialize the cipher at that particular point. As I said, it's a bit like a seed for a random number generator. So when we decrypt it, we do, instead of secret box, we do secret box open, and we pass in again the cipher text, the nonce, and the key. And doing the same thing with the AEAD function, we just pass in the nonce twice and the key. There are some variants of this. You'll find these ones with the IETF, I think it's the Internet Engineering Task Force. They define some particular formats to use with for encrypted content like this, and those particular implementations are compatible with the IETF specification for those. In future, there will actually be a function called this, AEAD encrypt. And the reason that it currently has these actual named algorithms here is because there's actually a competition going on at the moment called the CISA competition. And this is something that happens in cryptography quite a bit. They have competitions to establish what is going to be the implementation of choice for, say, a nationally sanctioned algorithm for something. Now, AES is a good example of this. The AES encryption algorithm was the result of a competition. Originally, the actual algorithm underneath it is a thing called Rijndal, which is like a Dutch word or something. I can't remember what it stands for. That then became the AES encryption standard. Now, we're still awaiting the results of the CISA competition. It hasn't finished yet, but it's probably going to be either AES 256 or CHA-20 poly 1305. But once that's been decided, Sodium will nail it to this function. So it'll actually make your code a little bit shorter. So then we finally get on to the two keys thing, which is public key encryption. Public key encryption is just extraordinarily clever. It really is. Bear in mind that until the early 1970s, all encryption was secret key encryption. There was no such thing as public key encryption. It's partly the advent of computers that have even made it possible. And it relies on some mathematics that just hadn't been invented until this point, and people hadn't occurred to them that they had to do this. And public key encryption is what allows us to have secure websites. It's just a stunning bit of imagination and theorization by the mathematicians that derived it. It was actually effectively invented by two groups of people separately, but because they were both working for governments in completely different places and it was all super top secret, neither one knew that the other had invented the same thing. But fundamentally, it has this thing of having a pair of keys instead of just one key. And they work together. And effectively, messages encrypted with a public key can be decrypted with a private key, and sort of vice versa. And it's also a critical component of key exchange. Now, one of the problems with this, with the whole public key encryption approach, is that it's extremely slow. It's orders of magnitude slower than secret key encryption. And so what you actually do is you use public key encryption, and all you use it for is to transfer a key from one side to the other. And that means that you've got the public key algorithm dealing with just a tiny weeny little piece of data. It's just the key itself. You transfer that from one side to the other. And once you've both got the same key, you can then switch to using secret key encryption, which is way, way faster. And that's exactly how TLS works. During the handshake at the beginning of it, it opens up this conversation, it sorts out which algorithms it's going to use, and then it picks the best one, transfers the key, and then switches to using the symmetric algorithm. And again, there are a whole bunch of popular algorithms to use for this in key exchange: RSA, Diffie-Hellman, and more recently, X25519. All of these are, well, RSA is slightly different because it actually is a cipher as well as being a key exchange thing. But Diffie-Hellman, you'll see all over the place. You'll see things mentioning DH occurs all over the place. So how do we do public key encryption in Sodium? Well, it has this whole bunch of box functions. Instead of being secret box, it's just box because it's the public key. And internally, it uses X25519 key exchange and the X-Salsa20 stream cipher, which is the symmetric cipher, and the Poly 1305 MAC to ensure integrity. How do we actually do it? Well, it's slightly more involved than using secret key encryption. But fundamentally, on each end, we imagine we have two nodes, A and B. On each side, we do the same thing. We make a key pair, and we extract the secret key and the public key from the pair on each side. And then we want node A to send a message to node B using B's public key and A's private key. So we have our message, and then literally, this is just string concatenation in PHP. It's actually far simpler than you might expect. We take node A's secret key and node B's public key, and the public key we can just go and get off their website. It's the first half of a TLS handshake, for example. But this is outside TLS. This is something you're doing it yourself instead of using TLS. You might be implementing your secure chat client or something. So you just tack those two things together. We make a nonce, again using secret box nonce bytes constant, and we feed the whole lot. We got the nonce here, and we just append the encrypted text with the nonce there. Now this is making use of the AEAD cipher feature of having some plain text embedded along with it. So we pass in the nonce to that as well, and the keys that we made by sticking them together, and that's our ciphertext. We send that over to the other side where we want to decrypt it. And here we do kind of the mirror image. We take our own secret key, which is the flip side of the public key here, and then we take node A's public key, which is the flip side of this key. So there's a nice little crossover of those two there. And we pass them into here. We need to extract the nonce, which so we tacked on the front here, and we knew how big it was. So we just used the same constant to strip off that chunk of data off the front. And similarly, we take the ciphertext and we just lock the rest of it off. And then we pass in those parameters into there, and we end up with the decrypted content. So that's the whole thing. That's all you have to do for doing complete public key encryption in your own code. Other cryptographic functions, key derivation. This is really just essentially how to do the password hashing thing again. I mentioned Sodium's quite keen on returning binary values instead of like hex strings from cryptographic functions, and the crypto password hash function does exactly that. It returns binary values, so that it tends to not be the kind of thing that you normally actually use, but you may want to use it for compatibility reasons or something. You can actually do the key exchange part that we saw during that public key encryption. You can do that bit all by itself. You don't have to follow up with actually transmitting a message. You can just use the public key encryption mechanism purely to transfer a key, and then not do anything else, not actually transfer a message at all. But it then means that in future, you can use that secret key because you know that the other end has got it. How key exchange works is amazing. It's so clever. In particular, the Diffie-Hellman algorithm that's used behind all of it. It's just a wonderfully elegant thing, and I don't really understand the maths behind it, but the actual principle is just amazing. There's a really good explanation on Wikipedia, and there's some videos on YouTube using color mixing as an example of the effective way that it does it. It's really clever. Another thing that you can do is digital signatures. And this is a little bit like using public key encryption backwards, where one of the problems with using a MAC to sign something is that in order to verify a MAC, you have to have the key. And that's a problem. Because if you've got the key, then sure, you can verify it, but you can also re-sign because it uses the same key. It's just like secret key encryption. Use the same key to verify as you do to create a new one. So that's a problem, but you can use a digital signature which effectively reverses the thing, reverses the public key encryption mechanism, which means that you actually end up not encrypting the content, but you still end up with a signature. And you can verify that using the public keys again. But that means that you're able to verify the content without having a key that would allow you to create a new key for some new content, because you don't have the secret key associated with it. As I mentioned before, there are a few little problems with the way that things have been implemented in PHP. The password hash function in PHP 7.2 actually already has the password argon2i, so it does the timing resistor, the sidechannel resistant version of argon2. But unfortunately, that implementation is provided by a different library called libargon2, which isn't included by default, so you can't really rely on it being there. So Sodium provides a better argon2 algorithm because it supports argon2 ID, but it's not used by password hash, unfortunately. There was a really good Twitter conversation just recently which might mean that this does actually end up happening. The argon2 ID version is actually being added in PHP 7.3, so that's good. But again, it suffers from exactly the same problem. Unfortunately, Laravel recently added support for argon2 passwords, and that would have been a great opportunity to solve that problem, to bridge that gap, but it just didn't really happen. But ultimately, you can get around it just by using Sodium's crypto function. I'm kind of out of time here. There's, I've got a few minutes. As a little example, one of the things that I've used this for is generating API tokens in Laravel. And the idea here is that I want to be able to have something where I can have people log into a website, but not have to store anything about their session on the server side. And that's a really great way of scaling stuff. Pretty much all scalable solutions have the one thing in common, is essentially offloading stuff to the client wherever possible. I think one of the best examples of that is Memcache. Memcache just scales absolutely beautifully, and it does it by putting all the intelligence on the client end. The individual servers have no idea that the other servers even exist, but the clients do. So here we get a, where are we? We have a user ID, and we do a JSON encode, and we do, I've just used the CHAR20 secret key encryption, and I just encrypt it, and I just tack the API token with the nonce and the encrypted content of it into the key that's passed back after somebody's logged in. And because this is encrypted, and we know that it's authenticated and we guarantee its integrity, it's safe to give it to the client. They can't tamper with it. So we give that to the client, and then if it's in a cookie or in an authentication header, they give it back to us, and then we can just decode it afterwards. So here's the decoding side of it. So they make a request to us, and we do something clever here. This is another Sodium feature, this mem0. One of the problems here is that we've got the key in memory. But once we've used it, we don't need it anymore. However, it's still lying around in memory. And a favorite thing of binary analysts to do is to try and grab the entire contents of memory of something and analyze the contents of it and try and find keys within that memory. So this mem0 function spots the space that's used by the key and overwrites it with either zeros or just random data. So that means that somebody doing binary analysis on it can't find it later on. So we then decode the value that we decrypted from here using the same keys, because it's both ends of this conversation are happening under our control. We've got the key, so we don't have to worry about the client. We give them something encrypted, they give the same thing back to us. And then we then verify that it is actually, basically, if they have tampered with it, the decryption will fail and we'll count them as not being logged in. So we then go, you need to log in before you do this. And then we can pass in, we can extract these two things, and we just check that it hasn't expired and that the user actually exists, and then we're happy with that. So that's an example of actually using the Sodium crypto functions in an actual practical application. One of the things about Sodium is the documentation, and unfortunately, you're going to see a lot of this. Sodium, because it's implemented in so many different places, actually has its own documentation. Fortunately, for the most part, that all works exactly the same in PHP as it does in other languages. So if you go and look at Libsodium's own documentation, you'll find stuff there. Now, I mentioned Scott Arkaszewski at Paragon. He's got really good documentation and lots of really great examples of how to use Sodium and some of the detail on the functions and so on. And I've actually been making a start on trying to actually write some of that stuff into the real PHP docs. However, it's been a bit of a learning process for me. I hadn't written any of the official PHP docs before, and it's quite complicated to get into it in the first place, and it's not really very clear how you have to do it. And the other thing is, I've written stuff and it's just sitting there. And I have no idea how to say, can somebody look at this? The other thing, it doesn't help, a lot of the PHP mailing lists don't actually work. It's not possible to sign up for like the documentation mailing list and say, hey, can someone go commit this, please? So there's a whole load of stuff just sitting there waiting to be merged, and I'm not really sure when it's going to happen. So I haven't been pushing too hard on that, but I wrote all the documentation for the password hash functions because they're probably the thing that is most likely to be used. So in summary, don't roll your own crypto. Don't use legacy crypto in new applications. Use Sodium if you're going to do any kind of encryption in PHP with the fundamental aim that it's trying to remove ambiguity and doubt from any cryptographic functions that you're using. And overall, Sodium really raises the security bar. If you're using Sodium in your app, you can be pretty much sure, certainly for now, that you're doing stuff right, you're not doing things wrong. You're not going to be vulnerable. So follow the documentation on Sodium's site and so on. But it does really need your help for the docs if you're up to writing some. And that's pretty much it. So, any questions? On here.
In case some of the algorithms that Sodium uses are becoming like breached or something like that,
Mm-hmm.
is it, will they upgrade? And if yes, how do they do that? Because I didn't see anything that shows like this uses that algorithm like you have in Unix password files, for example.
Yeah.
Prefix, which says this is the algorithm that I'm using.
Mm-hmm. Well, the password hash functions actually avoid that problem by actually embedding the algorithm in the thing. This is actually part of the difference between the binary password hash function and the text version. The text version embeds a little prefix. I don't know if you've ever actually looked at the prefixes generated like by the password hash functions. The ones generated by Argon are exactly the same kind of pattern. It tells you what the algorithm is, and the Argon 2 algorithm actually has two variables. It tells it basically how much memory to use and how much CPU to use. And so it needs to store those parameters in order for you to be able to recalculate the same hash later on. But that's embedded into the string that it generates. So in future, you will be able to still verify that, and it will know that it uses that particular algorithm. But any new ones that you generate will use whatever new algorithm it is. Now, on things like the secret key encryption, it's more of a problem, certainly. But generally, if you're doing secret key, you're probably in charge of both ends anyway. So that's not really a problem. And if it's public key, it's there's probably going to be a lot more headlines if someone breaks that. You'll know all about it a long way in advance. Any more? One over there. No, it doesn't actually. It actually does the reverse, weirdly enough. SHA 256 has some that nobody's actually found a working exploit for it, but there is a potential for more likely collisions in SHA 256. So SHA 512/256 is actually considered to be slightly more secure than SHA 256 is. But fundamentally, they're both 256-bit algorithms, and the SHA-2 algorithm is really pretty good for now. It's holding up well in the face of quite a lot of attacks and attempts and lots of theorization. Any more? No? All right, well, I guess we're done. Conference over.